Hello, in this podcast we are going to be describing human populations, and this is a change from the previous unit where we were just looking at populations in general. And in this podcast we'll be looking at populations both through equations and through graphs. Next podcast we'll be looking at the impact of human populations. We're going to start off looking at the history of the human population. Here we have a map of showing human populations from 2000 years ago, when the human population was about 300 million. And then we're going to go 1,000 years later at the year 1000, where the population grew by only 10 million people. And that's less than 0.1% a year. And the population actually dropped 300 years later because of the Black Death, which is the bubonic plague. But then beginning in the 18th century, late 18th century, the Industrial Revolution started to raise living standards and growth, so that in the year 1800, we reached 1 billion people for the first time. So it took us about 100,000 years since our species evolved for us to reach our first billion. So in the year 1800, about 65% of all people lived in Asia. That's 21% were living in Europe, and less than 1% were living in North America. And it took 100,000 years for us to reach 1 billion. It only took 127 years for us to reach 2 billion in the year 1927. And then from 1920 to 1950, the population hovered around 1% a year. And then in the middle of the century, with antibiotics and public health advances, that profoundly altered life expectancy, and that increased the number of children who could bear, so that in 1960 we reached 3 billion people. And this was brought about by advances in medicine, agriculture, and sanitation spreading to many places in the developing world. And in the late 1960s, the growth rate of human population hit an all-time peak of 2.04% a year, and after that it started dropping. But still, it was growing very rapidly, so it only took 14 years for us to reach 4 billion in 1974. And also in the 1970s, reproductive technologies were helping to bring down the growth rate. But even so, we were still experiencing a population explosion, and a lot of the explosion were centered in the developing world. And it only took 13 years for the 5 billionth baby to be born in 1987. And then 12 years for the 6 billionth baby to be born in 1999. And in 1999, Europe and Africa hold only 12% of the world's population. 9% lives in Latin America, 5% in North America. And Asia still holds the majority of the Earth's inhabitants, which is about 61%, or more than 3.5 billion people. If you project ahead to 2050, we're projected to have 9 billion people, and this may give considerable strain for the demand on food and water. And we'll be looking at that later on in the year, and also we will also look on why growth rates have actually been going down in the developed world. Now here we see the world population graphically. And you may ask yourself, what kind of growth rate is this? What does it look like? Remembering back to the last unit, is this the growth of an R strategist? Is this the growth of a K strategist? Well, it does look like the growth of an R strategist. This is exponential growth. But we project further ahead, we're seeing that we've reached our peak in 1960, and we're actually starting to slow down. So we really are K strategists. It's just, even if you look at K strategists, look at the beginning, it looks exponential. Thomas Malthus is someone who you need to know because he was really the first one to look at the effects of the exploding population boom. He lived in the early 19th century, and he theorized that the amount of food grows arithmetically while the population grows geometrically. So what does this mean? Here you see a graph showing arithmetic growth versus geometric growth. And you see how arithmetic growth looks like a line and geometric growth is exponential. Arithmetic growth grows at a constant rate. Geometric growth grows at an increasing rate. So arithmetic growth is linear Metric is exponential. So food increases ultimately or eventually will increase at a slower rate than the population. So eventually, Malthus says, population will outstrip supplies, and that will result in disease and famine, or the population will stabilize due to social factors, which is what it, to a certain extent, appears to be happening now. Now, the rapid population growth of the 20th and 21st century is due to a number of things you see here. It's due to increased food and more efficient distribution. It's due to, this is from the Green Revolution, which we'll be learning about later, and also due to better nutrition. Also improvements in medicine and public health technology, and improvements in sanitation and personal hygiene. Many, many lives have been saved by just simple things like washing your hands. And also safe water supplies. Used to be that one of the main leading causes of death in the world was diarrhea, which was caused mainly by cholera. And cholera is a disease that's caused by contaminated water. Sorry, but we have to come to math. We ran to some of this math. We ran into this equation right here, simple growth rate, in the last chapter, and so I'm not going to go too much into it, but we have here a variation of that, and that's percent growth rate, and that's just birth rate minus death rate plus immigration minus emigration divided by the total population times 100%. And over here I have a sample that's worked out, and to get the answer for that, you just simply plug the answers in. And here we have the birth rate minus the death rate plus the immigrants minus the emigrants divided by the total population. And there's our answer. You also may be asked for the intrinsic rate of growth, and that's an easier one to remember because you don't have to worry about the immigrants and emigrants. It's just birth rate minus death rate. Net growth rate is looking at it over a period of time, the later population size divided by the earlier population size. And the thing to keep in mind there is that if the net growth rate is 1, that means the two population sizes are the same, so there is no growth rate. Sorry, there is no growth at all of the population. If the population is doubling in that time, that means it would be 2. If the population is shrinking, then that answer would have to be a fraction, so it would be a decimal between 0 and 1. Population density is just population divided by area. And keep in mind here, I have two examples here to show what I want to keep in mind is that you see here's density of the United States worked out and density of California. And you see California is more dense than the United States. And the reason why is because our species does not settle randomly all side out. We clump. In the United States, we tend to clump around the coastlines. We also tend to clump around the cities. So we have a lot of people here, say in New York City, and if you go upstate, go out to western New York State, you'll find the population densities are much, much lower. Go out to, say, some states out west, and you can drive for miles and miles and miles and not see a soul. Birth rate and death rate are very similar equations. It's birth rate it's number of births in 1 year divided by total population, either times 100 if you're asked for percent, or times 1,000 if you're asked for the rate per 1,000, and same thing for the death rate. And I have an example worked out there for you. Rule of 70 is an important rule you need to know, and that tells you how many years it takes before the population doubles, and it's 70 divided by growth as a percentage. And it's important to write down as a percentage and not convert it out of percentage. Like if I would take that 1.07% out of percent, that means it would be 0.0107, and you don't do that, you just keep it as 1.07. So working this out, it would be 70 divided by 1.07, and that, when you work that out, that means that in California it would take 65 years for the population to double. Another equation is the annual percent rate of population change, and that's births minus deaths divided by 1,000 times 100%. And here I have an example of that. So that would be, where you work that out, it's just 19.15, which is the number of births minus number of deaths, 7.99, divided by 1,000 times 100%, and that would all equal to 1.116. Now that's not really the answer that's being looked for. If you look, because you have to keep in mind significant digits, and while 19.15 has 4 significant digits, 7.99 has only 3. So we have to use this with 3, so we have to make that 1.12. We have to round this last one. So this here is our answer. Now we come to age structure diagrams, and age structure diagrams we'll get into also in the next podcast also. And they are important because they can be used to predict future trends. And previously, we were just looking at populations. This shows you more because they show you the populations in each cohort. And a cohort are the population that are born in the same year. Like, for example, in the school, we also look at cohorts. Our school report card is mainly based on cohorts. Like, for example, when you come in the 9th grade, everyone who came in the 9th grade with you is in your cohort. And remember, in the 9th grade, you had to get 10 credits in order to move on to the 10th grade. Those who stayed in the 9th grade, you could say they were super freshmen, you moved on to the 10th grade. But those people who stayed in the 9th grade, even though they're still in the 9th grade, they're still in your cohort and are treated as such in school report card. So when we look at these age structure diagrams, if they're in color, frequently you'll see them in 3 colors like what you see here. And the bottom color that shows us ages 0 to 14, which are the children, the pre-reproductive ages. The middle color are usually ages 15 to 44, which are the reproductive ages, the ages which people have children. And then the top color are ages 45 to 85 plus, which are the post-reproductive ages where people generally do not have children. They may still be raising children, but they're not bearing children. So if we start off with this one over here, where we're looking at Kenya, Nigeria, and Saudi Arabia, this is what those ones typically look like. And you see it looks like a pyramid, and it shallowly goes up there, and you see how there are significantly more children than there are reproductive adults. So when these children grow up to become reproductive, that the number of reproductive adults are going to be quite a bit greater than what there is today. So that means that this type of age structure diagram is showing rapid growth. On the other hand, if we go over here and look at the one that shows what it shows for Austria, Denmark, and Italy, you see how the cohorts for the children, their population size is really right about the same as for their parents, for the reproductive ages. So that when these children grow up, the population size is really going to be about the same. So this age structure diagram shows 0 growth. And then we look in Australia, Canada, United States. This is in between the two, so that's showing slow growth. What would negative growth look like, where population is shrinking? In that case, you would see the the cohorts for the children, their sizes being smaller than for the reproductive cohorts. Now we come to the concluding questions. Number 1, what kind of growth has our species exhibited? Number 2, what did Malthus predict? Number 3, what is the rule of 70? Number 4, why are egg structure diagrams important? That concludes our vodcast, and I'll see you in class tomorrow.